SwayamPrabha. Digital India. Educated India.
So, welcome back to one more lecture on Introduction to Soft Matter. Last time we were looking at inelastic fluids, and we had said that when flow phenomena are dictated only by viscosity and elasticity is absent, then a suitable constitutive relationship becomes necessary. And in this kind of constitutive relationship, you have viscosity which plays an important role, but the viscosity need not anymore have a simple linear relationship with shear rate. And that is where the deviation from the simple Newtonian model occurs. So, let us go ahead and take a look back at this kind of a phenomena. And before that, we had also discussed the generalized strain rate, and what we had done was we had just started plotting the shear stress versus the shear rate, and we had drawn as one straight line, and this straight line is essentially representative of a Newtonian fluid. Now, on this diagram you can have another type of material whose shear rate graph looks something like this, and this we would call as a Bingham plastic. In a Bingham plastic you have a yield stress that this material can support. So, you have an yield stress here, and the material does not freely flow. So, there is no appreciable shear rate till you exceed a certain yield stress, but after you exceed the shear rate, the material flows almost like a Newtonian fluid. So, you have a relationship which looks exactly like a Newtonian fluid, but once the applied stress exceeds a particular critical value. A slightly different type of material here would look with a yield stress, but where this relationship may no longer be linear is what is called the plastic flows. So, this is your plastic. Here the material has a yield stress. So, the material starts to flow after a certain critical stress has exceeded, but then the shear stress does not behave linearly with shear rate. In fact, the shear stress decreases as the shear rate increases, or in a sense effectively the viscosity of this material decreases as the shear rate is being increased. So, this is an example of what we also often call the shear thinning phenomena, where the effective viscosity decreases as you increase the shear rate. And that brings us to another type of fluid, which maybe I will use black here, and this graph represents a shear thinning fluid. Also called as a pseudoplastic. You can see that in the shear thinning fluid there is no yield stress. So, it is actually behaving exactly like a fluid, but the shear stress is decreasing with higher shear rates. So, effectively the viscosity is decreasing with that. Okay. So, now you can imagine, so this is our control. This is sort of the line of separation, right? This is our well behaved Newtonian fluid that we have, this straight line right in between. And I've drawn all these on the other side. So you can guess that there will be something on this side as well, and that is the equivalent of that. Maybe I'll use a black one again, would be a material like this. And this is a dilatant without yield or a shear thickening fluid. So, this graph it has become pretty crowded, but it gives you an idea of the various important inelastic phenomena or inelastic material laws that are there. And these are important terms that you might see in a textbook. There are other terms as well, depending on how this graph behaves. So, we will not go into all of them, we are just going to try and give you a nice pictorial or a plot driven idea of what the various inelastic models can be. Of these models, one of the most important ones are this pseudoplastic category, and I will just make some space for me to write here. So, pseudoplastic, as we said, or shear thinning, polymer melts. So, we had seen earlier that one of the largest classes of soft materials or viscoelastic fluids that we have encountered, maybe the term soft material is more appropriate here, are the polymers. So, the polymer, so most of the polymer melts or solutions of polymers, they behave often as shear thinning fluids. So, polymer melts and solutions. When I say solutions, it means solutions of polymers are often shear thinning. Now, when we say shear thinning, we must understand that in a real situation, a polymeric fluid probably has viscoelasticity, which means it has both characteristics of viscous fluid and the elastic behavior. But when you use the word shear thinning, you must always remember that you are only describing the viscous part of the material, and you are implying almost nothing about the elastic part. And more often than not, that is usually considered, that can be considered, that the elastic part is maybe totally absent. In a theoretical model, that is possible, because you can create an artificial theoretical model which has only shear thinning, but in a real fluid that may or may not be true. So, you can have a polymeric fluid where there can be both elasticity, so both viscous and elasticity, but the viscosity part is shear thinning and the elasticity is somehow governed by some other equations. Okay. So, you have to remember that the word shear thinning only describes one part of that real behavior. Okay. So, now that made some space for myself. So, this issue of yield stress, so I am just going to write it down for you. This issue of yield stress is somewhat complicated by the fact. So, maybe at this time this is a good time to recall the original reason why we coined the term Deborah number, and we know that if you wait long enough, everything flows. Right? So, in a sense, if you wait long enough, even the concept of yield stress can then start becoming a bit vague as to what we mean, because if you wait long enough, everything is going to flow. So, what does this term even mean? So, this is somewhat complicated by the fact that if one waits long enough, everything flows. We will not address this in too much detail, but I will just simply say that when we say yield stress, it usually means in a sense sort of almost immediately you are looking at the response in a sort of instantaneous sense. So, I will leave it at that. Okay. Now, since we are going to be dealing a lot with polymers, it is and we have one lab session where we will actually look at polymer solutions. So, see, the shear thinning behavior is something that is very common there. So, while we have discussed the general nature of the graph, one has to, if you have to quantify the shear thinning behavior, you have to give a mathematical model for it. So, one of the popular models for shear thinning behavior is the Carew model. So, and in a Carew model, the equation that governs this is given as I will just quickly check what was the term I was using for. Okay. So, we have been using eta for viscosity. So, maybe we will just stick with that. So, eta gamma dot so your viscosity, when we wrote this in this way, it implies that your viscosity is a function of the shear stress, is usually written as one constant which is eta to the subscript infinity, and then you have a fraction which is given by eta naught minus eta infinity, and this is 1 plus lambda square gamma dot square 1 minus n by 2. Okay. And here I have to specify that this lambda is some time constant and it can or it need not be related to your viscoelastic time scales. Okay. So, lambda is just a parameter in this equation, and this equation relates a few quantities, and maybe it is best to draw a graph here and then explain. Okay. I will just draw it here. Okay. So, here this value, this intercept is also called eta naught or the 0 shear viscosity. So, in this model you have an initial time, initial part of the graph which behaves almost in a Newtonian fashion, and then the shear rate decreases very quickly with time. The viscosity decreases with shear rate very quickly. So, in this graph what you have is eta naught is the 0 shear viscosity, and the viscosity is more or less constant with respect to shear rate in the beginning. Then you have another section where the viscosity decreases sharply with increasing shear rates, and then it finally stabilizes to another value. And this other intercept and this intercept or this asymptotic value, this is your eta infinity or the infinity shear viscosity. Okay. So, this explains the few terms here. So, we have eta infinity here, this is the infinity shear viscosity, you have eta naught which is the 0 shear viscosity, again you have eta naught minus eta infinity in the numerator, and this is again the infinity shear viscosity. And then in the denominator you have lambda squared, lambda being some time constant associated with this phenomena. Gamma dot is the shear rate, and then you have a parameter n. Okay. So, this parameter n governs the shear thinning phenomena. If n is equal to 1, then you can see easily you get a Newtonian fluid, you get back a Newtonian fluid. And usually your n for shear thinning fluids, this model is meant only for shear thinning fluids. So, for shear thinning fluids, your n is lies between 0 and 1, right. So, we can see even from the graph that there are 3 basic regimes of this, and you can figure out what the regimes are from this equation. Okay. So, maybe we will discuss that in a little bit of detail. So, for example, you have this term in the numerator. So, let us go back to this. So, if this particular term lambda square into gamma dot square, if this term is much smaller than 1, then in the denominator you will have 1 to the power of something. So, you can see that when this term is very small, the behavior should be approximately Newtonian, right. So, from the mathematical model we can see that when is much less than 1, then is more or less eta naught, or you get a Newtonian behavior in the beginning, or for small enough shear rates. Maybe I will just put an approximately sign here. It is not exactly equal to 0, but it is approximately equal to eta naught. Then you have a region where this term will start to become comparable to 1, and that is where you will start to have appreciable shear thinning behavior, and that is when you will see. So, when is of the order of 1 or greater than 1, then non-Newtonian or shear thinning behavior is seen. And finally, if you go back to this equation, obviously when this term starts to dominate and becomes very large, then when this term becomes very large, this entire denominator starts to go towards infinity, right. So, in that case your is much greater than 1, and starts becoming okay. So, this particular Carew model, if you take the situation where we are looking only at the part where this shear thinning behavior is very dominant. So, if you are already in a range that the shear thinning behavior can be seen very predominantly, then you end up with what is called as a power law. You can devise another constitutive relationship which is called the power law fluid. Here your viscosity as a function of gamma dot is given by k times the absolute value of gamma dot raised to the power of n minus 1, where this k is a constant and n is the power law index. If you assume a value for n eta, you assume a value of 0. For high shear rates, you can show that the Carew model can also can be reduced to this particular form. Okay. But usually the power law fluid formulation is meant for calculating the viscosities in a given shear rate regime. Okay. So, now this brings us to another important idea that is often used in polymeric fluids, and to characterize polymeric fluids what we do is we often use two separate type of flows. Okay. So, there are two flows, two types of flows are used characterize polymeric flows, and one of them is called a shear flow or a simple shear flow, and the other one is called the shear free flow. So, today we will only look at in detail at the shear flow or simple shear flows. So, let us look at simple a simple shear flow is such a flow where the velocity field is given by. So, you will have a three components of velocity for any given general flow. So, for a simple shear flow we say that the velocity should be of the form u should be a sum gamma dot times of y. We will clarify why we are writing it as gamma dot, is basically some constant times y. The other velocity v and w, which are the other two components of the velocity, these should be 0. So, it should be a one dimensional flow such that the flow is a function of the x direction flow is a function of y, right. And in general this gamma dot can be a function of time. Right. Now, steady shear flows. So, when this is not a function of time, this can be a function of time in general, but when this is not a function of time, when this is a steady shear situation, steady shear flows are also called viscometric flows. Now, how are you going to cause such a flow? is a very simple way of creating this kind of a flow structure, and that is by taking two parallel plates which are separated by a small distance, and I will tell you why small distance. The bottom plate is stationary and the top plate is being moved ahead by some velocity capital U. So, this top plate is being dragged at a constant velocity. In that case, the flow here will look like this. In a laminar flow case, the flow, and if this is a height h, then gamma dot in this particular case is given by for a steady flow system. Now, this kind of a flow is very important because it helps us characterize some important quantities which are, we will go see that there are important material functions for polymeric flows and viscoelastic flows in general. Now, when you have this kind of a simple shear flow, your velocity gradient tensor, if you calculate that, this is simply my gradient of this quantity will have all zeros at all locations except for one case, which is the second entry here. Rest of all these entries will be 0. You can probably see that with see rest of all the velocities are 0, right. So, all the derivatives are also 0. This is the velocity gradient tensor. Now, in this particular case, if you calculate the strain rate tensor, then that is going to be, that is half times transpose. Now, this will have two entries, right. You will have the half here, and this gamma dot here will also appear here. The rest of the terms again going to be 0, and gamma dot is the shear rate, right, for this entire system. And you can actually quickly double check also if you want. You can calculate, for example, you can calculate d square, and you can see that that will actually be equal to gamma dot square 0 0 0 gamma dot square. And from this you can see if you calculate the generalized shear rate, then you find that it is just gamma dot in this case. But the important point I want to make is, we saw that for the Newtonian case, your extra stress tensor for Newtonian fluids the extra stress tensor is given by 2 eta times d. So, here you can look at the form of this matrix, and you see that all these terms are 0, right. So, the normal stress terms for a simple shear flow for a Newtonian fluid is such that the normal stresses in all the cases will actually, the total, when you calculate the total stress that will have, the normal stresses will only be minus p minus p minus p. So, all the normal stresses are actually equal in that case, right. Okay. So, this is an important point with respect to Newtonian fluids, that in a simple shear flow the normal stresses are such that they are always equal, but we will see that that is not the case for non-Newtonian or viscoelastic fluids. Okay. So, we will do that in the next class. So, we will leave it here for today. Okay. Thank you.